Good evening. The Hubble Space Telescope continues to astound us. Look at these pictures of quasars, thousands of millions of light years away, probably powered by immense black holes. It just shows the tremendous power of Hubble. The latest lunar probe was Clementine. It went round and round the moon, sending back excellent pictures of the entire lunar surface. And there's been one very surprising suggestion, that radar, carried by Clementine, had detected ice on the moon, inside some of the great craters near the moon's south pole, where the sunlight never reaches the floors at all, and where the interiors are always bitterly cold. Ice on the moon. Very interesting. Well, I must say it does sound rather unlikely. The rocks brought back by the Apollo astronauts and the Russian unmanned probes have shown no traces at all of hydrated materials. Now, one thing I'm quite certain, if there is ice inside these polar craters, it's not lunar. It doesn't belong to the moon. It must have been dumped there by an impacting comet. And I can see problems there too. If the comet also caused the crater, the tremendous temperature at impact would surely have vaporized the ice. And if the crater were there already, it would be a very convenient comet that plunged straight into it, the bomb falling straight into the bucket, so to speak. So frankly, for the moment, I reserve judgment. We simply await the results of future research. And now, on to our main topic. On the 18th of October, 1989, the Galileo probe was launched to the planet Jupiter. It had to go by a rather roundabout path, rather like going from Brighton to Bognor by way of Carlisle, and on the way it made 2 forays into the asteroid belt and sent back pictures like this. There's the asteroid Ida, together with its tiny satellite Dactyl. But eventually, last December, Galileo did reach Jupiter. It was made up of 2 parts, an entry probe and an orbiter. The entry probe plunged into Jupiter's clouds and sent back priceless information for the last few bits of its life. Meanwhile, the orbiter went round and round Jupiter and started sending back pictures of the 4 Galilean satellites, Io, Europa, Ganymede and Callisto. And the results have been very interesting indeed. At this stage, I'm delighted to welcome back one of our regular visitors, Professor Garry Hunt. Welcome back, Garry.
Hello, Patrick.
Well, a little while ago, we met on this program and we talked about Galileo. Since then, what's new?
A great deal. A year ago, of course, we were just looking at the probe and the entry into the atmosphere and just wondering what the orbiter would do as well. But we have those results now of the probe, and they've told us a great deal about the atmosphere, its composition, and about the structure as well. Let me just refresh you what we actually have learned. Remember, this probe, this 2.5 tons of instruments, was whizzing towards Jupiter at a great speed, more than 100,000 miles an hour, 50 times faster than a rifle bullet. In a matter of 2 minutes, slowed down with its parachutes and such like to a mere 1,000 miles an hour before going into the clouds. And as it went through the clouds, it measured the atmospheric composition. And we've learned, what we've learned actually about it is really quite fascinating. Firstly, helium. That was the important part. We had estimates from Voyager. We weren't quite sure what it was like. But we now know that there's about 24% helium. Therefore, the hydrogen-helium ratio is like the Sun for Jupiter. And therefore, Jupiter is quite different from Saturn. So there's an important relationship. Now the changes come along. We've found other things like carbon, oxygen, and sulfur, and some of the noble gases. But when you look at these ratios, we also get some important clues. The ratio of carbon to hydrogen, sulfur to hydrogen, are actually 2 and 3 times greater than that we find in the Sun. So whereas the hydrogen and helium said that Jupiter is like the Sun, these ratios says that Jupiter is not like the Sun, which therefore we can only interpret that as such that Jupiter's atmosphere has been bombarded by other objects like comets and meteors, and that may have actually helped to change some of its actually atmospheric environment.
Well, we saw one impact, Shoemaker-Levy.
And I think that's a very important one. That's an indication of what has happened recently, and obviously has happened throughout the origin and lifetime of the solar system. At the place of entry, there was less water vapor than we found before, but let's remember, water vapor is very changeable. It condenses out, it precipitates and changes the whole environment, so this may not be something you can measure in one location. The probe itself went on for 62 minutes, got down to a pressure that's 24 times that of the surface pressure of the Earth, temperatures of 150 degrees centigrade, extremely hot temperatures. But the important part was lightning. We saw 10% less lightning than Voyager observed, but bear in mind, this is 6 degrees north. Voyager's observations were 45 degrees north, so they're not the same place. The probe itself did survive, just. The shield, 2/3 of it was actually destroyed during entry, but it did give us enormously interesting results. Also, even before it got to Jupiter, interesting results as well, because around Jupiter is this huge magnetosphere, trapped ionized particles of helium and other heavy gases as well. And what's interesting about that is that they actually extend down to within 4/10 of a Jovian radii, quite different from things we've observed before. Again, captured material also. So Jupiter, like the Sun, basically in terms of helium, but not like the Sun in some of the other material it's captured.
So certainly the entry probe was a great success. And meanwhile, the orbiter is going around Jupiter, studying the planet, and also the 4 big satellites, the Galileans, Io, Europa, Ganymede, and Callisto, which are big. I mean, they're planet-sized. As you can see there, Ganymede is actually larger than the planet Mercury, and Callisto nearly as large. Io a bit larger than our moon, and Europa just a bit smaller, and they're all different. And of course you can see them all with a small telescope, and it's fascinating to watch them. So Gary, what in fact is so special about the Galilean satellites?
I think it's rather sad that we actually call them satellites, because in the other normal circumstances we would call them planets. They are huge bodies. True. And the fact that they are so big is important to us, because the whole orbiter mission is making use of their size to change the orbits in the way we normally do for planets, and actually build up the knowledge of the Jovian system. But before we talk about the science results, Patrick, let's talk about some of the important engineering things, namely the communications, because Jupiter satellite system here is being observed by an orbiter which is a bit like a whispering giant. Galileo's antenna failed early on. We were very worried if we'd be able to get much data back, and this obviously was going to be a great concern for the entire science study. But in fact, NASA has been incredibly inventive. What they've done is to use the 2 powerful radio telescopes at Goldstone, 3 in Australia, link them up together so they're working together, forming a huge array. And as such, that has the effect of really helping to raise the data rate from just being a few bits per second to kilobits per second. So we're actually getting much more of the data than would otherwise be available. Also compressing the data, in other words, transmitting only that which is of scientific importance, not transmitting therefore dark sky. We're able to get a lot more data back from these very dark reaches of the Jovian system, which otherwise wouldn't be impossible. So at the time of closest approach to each one of these satellites, we'd be able to get back a lot of information which we can now discuss, which are really changing our mind about the Jovian satellites.
And so Galileo entered a closed path around Jupiter and began sending back data.
Yes, and I think the important part is the way the actual petals are built up, because as the spacecraft moved past Io, it dropped the probe and then went on the path using the satellites to change the orbit. And the first encounter of closest approach of this set was to Ganymede. And at Ganymede, which flew by early in the summer, we had a chance to really sort of change our understanding. Hubble, of course, is always here. We're able to use the Hubble pictures to observe each one of these bodies continuously, all the time, at different wavelengths, and actually complement what we were learning from the spacecraft. But it shows some areas are light, some areas are dark. Perhaps not very important from a geological point of view, but it can help about atmospheric information and gaseous composition in that neighborhood. The trouble with Voyager is that while we did observe these satellites, geologists were very frustrated because at 1 kilometer resolution you cannot understand the processes involved. You start to see dark areas, some areas of large craters, sunken craters, bright features as well, which suggest that there is some motion in that surface. It's not just one of bombardment, but really what's going on at high resolution onto Galileo, which actually can observe these objects down to resolution at 50 meters, beginning to get down to the scales that they actually want. And you can see it's even more complex. Some of the rills we've seen before we know are about 700 meters high. And when you go into the highest resolution that we got during the encounter in September, you can see that you have these lot of structures, as if people have dragged claws across. Small craters there have been taking place through the impact. There's a larger feature there too. But this is, again, a crater which has ice involved in the satellite, which have been changing some of those surface features. And when you project the images again from a different direction and look inside the craters, you can see they're quite shallow. And an indication of what is taking place is the impact can in fact be breaking up the surface, perhaps releasing some of the water and slushy material, helping to smooth it away. So we're not going to get the large features we see on our own particular planet. And again here, when you look at this particular area close up, again resolutions probably about 50 meters, you can see very bright white areas around the craters of ices there as well. So a complex geology which even at 50 meters is going to be difficult to unravel, but are showing just how complicated Ganymede actually is.
And that is, of course, a weak magnetic field, rather surprisingly.
That is a surprise, because we normally associate magnetic fields with rapidly rotating bodies. and Ganymede is not one like that. So we have the problem of what is the dark material. We have oxygen around the atmosphere, so there's perhaps a very thin tenuous atmosphere, and some weak magnetic field. So the information has gone up, so have the number of questions.
Certainly. Well, Ganymede was first on the list.
And then on to now, Callisto.
Callisto, yes.
And as the orbiter has gone through Ganymede, we had to change the orbit. And next aiming point to get close to was the flyby of Callisto, which is the outermost of the Galilean set of satellites. There is perhaps one word that describes Callisto from Voyager, and that is moon-like. We've seen it before, and it's all been heavily cratered. And really the question is, what happens if you see higher resolution? What you have here is Voyager are the outside ones, which you can see are low resolution. The middle part was the longitudinal region that was missing, that was not possible to obtain during the Voyager flybys.
That was taken by Galileo.
And this has now been taken by Galileo. So the outside in 1979, the middle part in 1996, difference of resolution of over a kilometre to a few tens of metres. What's happened? You just see more and more craters. So it really is an ancient cratered terrain. How old that surface is obviously now what we want to look at. If you look in the middle of it, you actually see a very bright crater. You see white striations coming from it, perhaps that's ejected material. But Callisto is certainly moon-like, heavily cratered, a whole range of crater sizes on it.
There's one very important difference, though. Callisto has an icy surface, and our moon certainly hasn't.
Well, that is certainly the case, and this is why we obviously going to see a different sort of albedo features on it as well, and it may also relate to the size of the craters, their depth, and also their general shapes as well. So this will affect the actual shapes of those craters because of the actual geology that's there.
Well, both Ganymede and Callisto are icy and cratered. Not so with the next satellite, Europa, which is very different.
Yes, this is the next major encounter that the orbiter will have. In fact, the actual encounter date, Patrick, is the 19th of December, and you can see with the petals building up, this is the approach that the orbiter is now on, a few days away. We know already from the Hubble Space Telescope what's happening recently, and you can see light areas and dark areas. But the important part of Europa, as you said, it's icy. It also is one of the brightest objects in the solar system. And the Voyager pictures of Europa really are almost perplexing. Very bright, clearly icy, highly reflective, striations, long linear features, no evidence of craters. And the question was, were we seeing those as the craters because we didn't have high enough resolution pictures? As we start to go in with the pictures from Galileo, they're showing what even more complex patterns. And in fact, what you're beginning to see is you can see a bright white area at the bottom. You can see a lot of linear features crisscrossing. Some areas of dark areas, obviously it relates to resurfacing because this thing is highly reflective. It's rather like some of the polar regions we see around the planet. Look at the equatorial areas. You can see close up as these lines literally cross. So what it strikes me as we're seeing is the top of some sort of ice sheet. And in fact that there are pressure patterns because of the gravitational forces there. They're buckling, perhaps there are ice plates 50, 60 kilometers across that are breaking up and perhaps reforming because there may be water material coming out from inside of Europa and in the cold area then sort of welds everything together and obviously resurfaces it as well.
What do you think of the suggestion that beneath the icy surface there might be an ocean of actually liquid water?
This certainly is consistent with the models of Europa, which itself could then have quite a large rocky core. It'd also be consistent with its high reflectivity, the very tenuous amount of oxygen we found around there, and of course that we definitely have some suggestions of the icy materials on the surface. The higher resolution is going to be extremely important, but how much we can strictly interpret by not actually going there is obviously going to be one of our major limitations.
Well, there was even a suggestion that this subterranean ocean might contain life, but I feel highly sceptical about that.
Well, it's always a danger. Every time you raise water, people start thinking of life, and I think that's something we should be careful about.
I quite agree. Well, so much for Europa. Then, of course, the next satellite, Io, is different again. Here we have the violently volcanic satellite.
Well, Io is important in the sense that, again, it's different, as you say, from the other satellites. We do not have a close flyby to get from pictures. There was a close flyby when the probe was dropped off, but we know from Voyager what it was like. But the thing about the Hubble Space Telescope is that we can actually monitor the behaviour of Io over a period of time. That is Pele, a volcano, the very bright object in the middle, which we can relate back to previous pictures, and we can monitor the changes of the brightness and other characteristics with time. Now with Voyager, this is where the fascinating was. Remember, the original idea was Io was going to be highly cratered, and of course it was the exact opposite. There were 9 active volcanoes discovered in 1979. We can see Pele very brightly there. So the question is, what's happened between 1979 and 1996? And indeed, what's happening during 1996? Now look at these particular pair of pictures. Voyager on the left, Galileo on the right. If you take your eye up towards the equator and then move up in a northwesterly direction, you see how there's a white area and a dark area, which has changed dramatically between those two pictures. Move across that white ring, that's Pele, an active volcano. And if you now get into the next picture, which is Pele close up, look in the middle, you can see how the vent has changed. It's actually shifted by 75 kilometres between 1979 and 1996. Go to the next sequence, we can actually see how matters are changing between the two missions and within the mission. Top left-hand corner is Voyager 1979. The bottom left-hand corner is June 1996, and that's Galileo. You can actually see quite a large number of surface features that have changed. There's a large dark area in Voyager which is no longer there in the Galileo picture. Move to the top right-hand corner. We've now gone from June 1996 to September 1996. And again, you can see, that's a picture to simulate what Voyager would look like, differences again in some of the dark areas. And the bottom right-hand picture is again September 1996. That's Galileo looking at longer wavelengths to show different surface features. So our local features are changing in the time scale of Voyager to Galileo, and then of course onto the Galileo mission itself.
Of course, these are not like our volcanoes. These are sulfur volcanoes. What drives them, Garry?
Well, this is boiling sulfur and sulfur dioxide being vented and squeezed up from the interior. In fact, when you look at the next picture, you can get an indication what they look like. Here is Pele, and changing with a matter of months during the Galileo mission. You can see how that bottom indentation has actually changed. And if you look at the next sequence and follow your eye, particularly along the bottom set, you can see as it moves towards the limb, it looks rather like a sort of the water sprays that we have in our gardens, a very small plume being vented up, being pushed out. And of course that's flowing, that's the lava that's flowing out onto the surface, also putting material, and it's putting sulfur type material into the atmosphere, some of which is actually trapped around Io and extending up to levels of 100 kilometres or so and not being swept away by the magnetosphere, which is a surprise.
Well, Galileo is still going around Jupiter. What next?
Europa in a few days' time, and several other encounters with these major satellites over the course of next year, so that by December of next year we will have had a total of 11 major orbits around the Galilean and Saturn satellites to give us a whole new understanding of them, perhaps a new understanding of their geology, certainly their atmospheric and interactions in the magnetosphere. Our understanding of Jupiter and its satellites and the environment is clearly changing.
So there's no doubt at all that Galileo has been an outstanding success. Garry, thank you very much.
Thank you, Patrick.
Don't forget, if you want the latest astronomical information, then dial up our information line, 0891 800 or CFAX, page 620. I want to come back next month. I'm going to be joined by Professor Glenn White of Queen Mary and Westfield College, and we're going to go right outside the solar system and talk about the centre of the galaxy. And since this is our last programme of 1996, I hope it's not too early to wish you all a very Merry Christmas and a Happy New Year. So until 1997, good night.